This lecture is about advanced exploitation techniques in the context of ASLR-related attacks and defenses. So in the diagram that I showed before, this is the right-hand branch. So what happens here is basically that we have ASLR and a bunch of similar defenses. And academics managed to find all sorts of ways to break these defenses. And then again, academics looked for defenses to prevent those attacks. So this is one of the branches, the other one is CFI, which I will discuss later. Now, what is the threat model that we're assuming here for these attacks and defenses? So the thing here is we already discussed exploit mitigations. However, these exploit mitigations were not practical. The overhead was too large to basically deploy a full set. Now, what is a threat model? A threat model defines when the program is considered secure. Or in other words, what do we need to defend against to know that we're done? So, in this case, we make the following assumptions. We assume that humans will make mistakes, which means that we must assume that there are bugs. We assume that comprehensive mitigations are not deployed because of the overhead or compatibility issues, which we discussed in the previous lecture. We assume that these exploitation techniques eventually lead to an arbitrary read and arbitrary write primitives. So for these defenses, we try to make sure that the program remains secure, even in the context where an attacker already has arbitrary read and arbitrary write. We also assume that there's enough code available for a full set of ROP gadgets that allows us to do arbitrary computation. Now this is actually a very low bar because it's very easy to gather gadgets and be able to construct a ROP chain in practice. And finally, we assume that arbitrary code execution leads to privilege escalation. In other words, the security property that we're trying to prevent here is not messing around with the stuff in the address space, but it's executing arbitrary code to achieve some goal. Now, the attacker can do arbitrary read and write, and we must prevent the attacker from using this to launch a ROP chain. So in the diagram that I showed before, this means essentially blocking the second step. Now there are multiple ways to do this, and the ASLR type of way is one of them, where we basically try to hide the gadgets, and the other one is CFI, which I will discuss later, where we try to block usage of the gadgets. In the earlier lecture on application security, I already discussed ASLR, but let me give you a very brief recap to show the parts that are important for this lecture. So ASLR moved the base of each section in the binary image to a random address, which means the text section containing the code starts at a random address, the stack starts at a random address, and so on. Now this means that a ROP chain is no longer possible because we don't know the addresses of the gadgets that we're supposed to point to. So this, in principle, would then prevent an attack because we can no longer threaten security by executing arbitrary payload. However, as I mentioned, leaking even just a single address reveals all the addresses in the section. We can easily compute them if we leak just a single pointer in a section. Now, even just the threat model arbitrary read already breaks ASLR. The question, however, is where to read. Now, in practice, this is typically very, very easy. Because if we have only a single buffer overflow or something like it that works with a relative offset and that can perform our arbitrary read, then we're already there. We can easily find a pointer to leak, in this case, in all practical scenarios. So ASLR is easily broken within the threat model. It's insecure. What can we do to make ASLR more secure? Now, since we were able to compute all the addresses in a section using just a single address, what we need to do to fix this is to randomize also all the relative addresses. In this case, we can no longer derive all the pointers from a single pointer because we don't know the relative addresses. So we can achieve this, for example, by shuffling around functions or even parts of functions, so-called basic blocks that are defined by the points where there are control transfers. So we can shuffle around the functions. We can also rewrite the functions, for example, change the registers that are used. If you do this, it makes no difference in the meaning of the program. Replace instructions with equivalent instructions, or even insert random NOP instructions, no operation instructions. Now, if we rewrite the functions like this, we shuffle them around and so on, all the relative addresses will be different, and we will not be able to predict them. So, we can no longer derive a pointer from another, and this means we can no longer construct a rob chain, right? Well, that is what we assume, but it turns out it might be different within the threat model of arbitrary read and arbitrary write. Well, it turns out that even perfect fine-grained ASLR can easily be broken, and it can be broken with a technique called JIT-ROB. This slide provides the assumptions that we make, under which we can perform a JIT-ROB attack. First of all, we assume that all the important defenses, at least at the time that JIT-ROB was published, are enabled, including data execution prevention, which prevents us from doing a shellcode, and also fine-grained ASLR. And fine-grained ASLR in this case is modeled based on the capabilities of all the fine-grained ASLR designs there were at that time. So essentially the perfect version of fine-grained ASLR. We assume that these are present, and we will show that JIT-ROB can beat these defenses. Now, additionally, we have some requirements. In particular, the attacker must be able to leak at least one code pointer, which is also what was the way in which we broke ASLR before. We must be able to leak data given an absolute address. So this is an arbitrary read vulnerability. And, this is important, after the leak we must be able to continue to interact with the vulnerable program. So we should be able to adjust our behavior based on the leak. And this is critical. Now, how do we perform the JIT-ROB attack? First of all, we use the code pointer or pointers to read the code. And given that the code is executed, we know that this is basically sequential, at least by default. If the code goes somewhere else, we'll see it from the code. So we can use the code pointer to read code, and afterwards, unless we find an unconditional branch, we can just continue reading and reading more of the program. Now, while reading the program, we also find branch instructions, for example, or other memory references. These we can use to derive more code pointers. Well, if we keep reading them, we eventually get a good view of the code that is there in the memory image. And even if it's randomized every time, because we can continue to interact with the program, we can still continue to identify the gadgets. And we can use those gadgets to compile a ROB payload on the fly, which is why we're talking about JIT-ROB, just-in-time ROB. So we're leaking not the pointers in this case, because we don't know where the gadgets actually are. So just leaking the pointers is not enough, but we leak the actual code as well. And then we use this code that we read to construct our ROB chain. So after this attack was presented, people began thinking about how can you prevent such an attack. Well, one of the ways to prevent this attack is the XNR approach, which means that you prevent code from being read. So any code that's executable is not readable, and vice versa. Now, JIT-ROB relies on being able to read the code, so this should prevent the attack. Unfortunately, x86 does not allow one to do this. x86 provides the following page settings. So a page can be present or not present, read-only or read-write, and executable or non-executable. Well, this means that any page which is present is also readable, and any page which is not present cannot be executed. Hence, any executable page must be readable on x86. Now, so what is XNR? XNR is a clever trick to make executable code non-readable, despite the lack of architectural support, because there is no way in x86 to perform this normally. The solution in XNR is simply to mark all the code pages as non-present. Now this means every time you attempt to either read or execute these pages, it results in a page fault. So the page fault tells the operating system that the program tried to execute or read some data that was not present in memory. The operating system then gets a chance to map this data in. Next, if this turns out to be a read, then we get an exception. So the operating system is able to tell whether this was actually intended to be executable code. Now, if this is executable code that the program was trying to read, the operating system knows that something is wrong, because this executable code was not supposed to be able to be read. So the operating system raises an exception. For example, it might send a segfault signal to the application. Well, if it turns out the operation we're doing is execute, then we mark the page as present in the page fault handler, which means that from that point onwards, the program will be able to read the page as if nothing and execute the page as if nothing happened. Now, we can see the scheme here. So the MMU detects the access because the page is not present. This happens here. Then the page fault handler determines which type of access this is. Based on that, it handles it by either marking it readable and executable because it will be present, or it will raise an exception in the next step. Now, we don't want all the code to become readable over time, because any code that is executable is still readable. What do? Well, we keep a list of pages that we mapped in, and when too many pages are mapped in, we simply start taking the first one, so we use a first in, first out ordering, and mark it non-present again. So we have a list of n pages that are currently mapped as present, and all the other pages are mapped not present. When the list fills up, we take the first entry and map it as not present again. So there is a security parameter here, which we call n in this case, and so n specifies essentially the last how many pages are kept readable and executable. The higher n is, the better the performance, because this means there are fewer page faults, but also the less secure, because there are more pages mapped in that can now be read if there's a vulnerability on one of the pages. Now, the overhead is just 2.2%, even at n is 2. If we increase n, the overhead can be made even less. So this approach is actually very efficient. But the question is, of course, is it also completely effective? As you no doubt expected, the answer to this question is no. Or at least in some cases, we can still be able to generate JIT drop attacks. So this is in the case that we actually have fine-grained ASLR in perfect implementation, as well as functional XNR defense. So the issue here is that we can look at specific types of programs, in particular targeting programs that actually generate code. It turns out that this includes a very important class of programs, namely browsers, because every browser includes a JavaScript engine that uses JIT techniques to compile the JavaScript code to executable code for the target system. Right? So even if write XOR execute is enabled, we can construct code in these programs. And these programs are very important because they're a big part of the attack surface of a client machine. It turns out that JavaScript code is actually compiled to predictable gadgets. So when we write the JavaScript code and we know the target platform, we can predict what the resulting machine code will be. This includes, interestingly, constants in JavaScript code. So if we have a constant in JavaScript, it must appear in the final executable code as also a constant. So this is obviously an issue because it would be easy to inject a gadget followed by a return instruction. Short gadgets would easily be includable in constants. So this is an issue, but this was already solved by the time blind jitrop came out. So modern browsers do so-called constant blinding. Rather than including the literal constant itself, they generate a random value and XOR the value with this random value. Now, they also XOR the value back again when executing, so this means we get the original value back, but it's not encoded anywhere in the code. So this takes away one of the effective ways to construct gadgets. Now, it turns out, as the blind jitrop authors have shown, that even just implicit constants allow you to give predictable gadgets. For example, if you write code in such a way that you get branches with predictable offsets, then you can use those offsets as predictable gadgets. And you can make sure that they match the numbers that you want to have. And this way you can generate all the opcodes that you might need for a ROP chain, even in the presence of fine-grained ASLR, as well as a defense like XNR. So we can still construct the ROP chain. Now, how can we prevent stuff like this? So another approach to deal with the weaknesses of ASLR is to simply make sure that no sensitive pointer can ever be leaked. So this is the approach of code pointer hiding, and the paper on this provides actually two different methods which do this. One which is stronger and the other which is faster. We'll first discuss the more secure method. Now, the idea of this approach is that full memory safety is expensive. Right? We've seen the lecture on vulnerability mitigations, and it turns out that doing full memory safety really costs a lot of overhead. We cannot realistically do this. Instead, what code pointer integrity proposes to do is only protect the most sensitive data using full memory safety. Now, you ask, what is the sensitive data then? Which is the data that we care so much about? Well, since our goal here is to prevent arbitrary code execution, and we've already blocked shellcode using write XOR execute, the most sensitive thing is actually the code pointers. Because if we cannot change a code pointer, then we cannot execute arbitrary code. So, also, it turns out if we protect just the code pointers, it's not enough. Because we could actually manipulate a pointer that points to a code pointer and have it point to something else. Then again, we are screwed, which we don't want. So, also pointers to sensitive data must be protected. Keep in mind here that sensitive in this case is recursive. So a pointer to a pointer to a pointer to code is still sensitive. Finally, anything else that contains the sensitive data, such as structs and arrays, must also be protected. So all of this must be protected using full memory safety, and then hopefully we reduce the overhead, but still protect all the important stuff. Now, this is exactly what code pointer integrity, or CPI, proposes to do. So it has a static analysis which is based on the types of variables to identify the sensitive variables. And essentially, as we already know, static analysis is incomplete, but it resolves this by simply assuming if it cannot tell whether something is sensitive or not, we must assume it's sensitive. This is the safe option to take. So if we mark something as sensitive and it really is not, then the program is still safe. It's just a bit slower than it would otherwise have been. Now, all the sensitive variables that we identify like this, we store in the so-called safe region. Now, the safe region is only accessed using comprehensive memory safety. So, for example, any array indexing is checked. Right? We cannot go out of bounds within the safe region. We cannot do use after free within the safe region, and so on. So now we have the address space split in parts, both the regular region and the safe region, and the way we access memory is different. Now, of course, only the regular region contains the code, because this is in itself not sensitive, as we cannot change it anyway, right? So the code is in the regular region, but the heap as well as the set stack are duplicated. So we have a number of unsafe stacks in the regular region and the safe stacks in the safe region. And now the safe stacks are protected using full memory defenses, and they are the only ones where code pointers are allowed to be stored. So this is all very nice, but now what happens if we have a buffer overflow in the regular region and we use this to access the safe region? This way, obviously, we can bypass all those strict memory defenses. So there must be some way that we're preventing this. And indeed, there is. We randomize the base of the safe region to make sure that the attacker cannot know where the safe region actually is. And then do consider that any pointer to anything in the safe region is sensitive. All of them are stored within the safe region and never outside, which means that we cannot leak this information. Now you might wonder, how do we actually access the safe region if we don't have a pointer to it? Well, we use a trick. So the x86 architecture has retained in 64-bit mode some of the rudimentary features that used to be in the 16-bit CPUs. And one of them is segment registers. And there are two segment registers available which have a base and which basically add the base to any access within the segment. Now, if this base is the base of the safe region, we can simply access anything in the safe region without needing an explicit pointer. So this is a perfectly safe way to do this. Now, moreover, the paper also defines so-called code pointer separation. So code pointer integrity should ensure that we can never change a code pointer because they're all in the safe region and any way to access the code pointer is protected. Now, code pointer separation is the weaker twin of CPI, and what it does is it stores only the code pointers themselves in the safe region. Now, this is considerably faster, especially for C++. While in C, function pointers are typically explicit, in C++ we have virtual functions, and if they get called a lot, it means that we have to go through the safe region a lot, and we have to do this for every object access, because every object contains a pointer to the vtable, which contains pointers to functions. So as you can see in C++, we're using a lot of memory safety, which introduces a lot of overhead. So CPS is faster, but it's not completely safe, because we can still indirectly change a code pointer by changing a pointer to that pointer. Performance-wise, CPI has some significant overhead, although it's not excessive, 8.4%, and CPS, even though it's not perfectly safe, it still provides some significant safety at only 1.9% overhead, which is actually very good. Well, it turns out not only CPI and CPS rely on using information hiding by randomizing the location of a region, but many defenses actually do this. For example, shadow stack and other versions of context-sensitive CFI, which we will discuss later, also require some secret storage that can only be accessed if we know the pointer that points to the base of the region. This is very common, and the typical approach to hide information is to hide the hidden region at a random address, access it through a segment register, and then make sure we never store pointers to the region. So this is something all those defenses have in common. Now the question is this something that we can break? And as you might expect, the answer is yes, we can break this. Now this is what the memory layout is typically like in the situation where we have a defense that relies on information hiding. So we have all the relevant stuff at the lower addresses, and there's a very large chunk of the address space. As we can see, typically this chunk of the address space is at least 130 terabytes, and at most 131 terabytes, so this is huge. And somewhere within this region is the hidden region. Now, we want to find this hidden region as an attacker. The approach that we can use is look at the size of the hole. If you can figure out how large the hole is, then we can compute the location of the hidden region still. So, is there a region to find the size of the hole? It turns out that yes, there is an efficient way to find the location of the hole. And this is using so-called allocation oracles, which were introduced in this paper, which was written again by the VUSEC group. Now, there are two kinds of allocation oracles that we can think of. The ephemeral, which temporarily allocate a buffer of an attacker chosen size, and also a permanent oracle, which permanently allocates such a buffer. Well, these kinds of oracles are actually very common in software, because any time that an attacker provides some data which is arbitrary size, then there needs to be memory allocated to store this data. So another thing to consider is that even if we don't have a permanent allocation oracle, if we're clever enough, we can actually turn an ephemeral one into a permanent one, simply by partially performing an operation and then keeping open the connection to the program, so that the ephemeral region is never deallocated, or at least not while we're working on whatever we're doing. Now, an important observation or an important assumption, which is also what makes these gadgets, essentially, what makes them oracles, is that we can observe whether or not the allocation succeeded. So the attacker is able to make sure that the program performs an allocation, and then it can check whether or not the allocation was actually successful. Well, if we meet these assumptions, how can we use this to actually break any information hiding based defense? We start by searching for the size of the largest hole. Now let's try a certain allocation size n using an ephemeral oracle. So we send some kind of data to the program that causes it to temporarily allocate a buffer of size n. Now, if this is successful and we can allocate the buffer, we know that the largest hole is at least n bytes. If it fails, we know that it's smaller than n bytes. Now, we can do a simple binary search, trying different values and very quickly finding out which is the size of the hole. The nice thing here also is that we don't actually crash the program at all, so we don't have any opportunity for the program to re-randomize. Now, to find the size of the other holes, this is where we use the permanent allocation oracle. So we perform a permanent allocation which fills exactly the largest hole that we just discovered, and now we perform the binary search again for the next smaller hole. So in this presentation I've shown a number of attacks as well as a number of defenses mitigating those attacks, and we can see a cycle where basically each time the attack breaks the previous defense. Now, the important thing here is that all these ASLR related defenses are in some way related or based on hiding information. And it turns out that leaking information is much easier than one would think. So for example, the allocation oracle looks like a perfectly innocent code construct in a program typically, but it turns out it's a way that attackers can use to leak important information that allows them to bypass defenses. So leaking information is much easier than you think, which means that trying to protect your system by keeping secrets is a losing proposition. Doing full protection using this approach is very hard. And even then, we did not yet consider so-called side channels. So side channels are often an even more effective way and harder to mitigate to leak information about a system. An example of a side channel would be cache timings. So if we accessed some memory before, the access will be faster. And this is a way we can use to try and see which memory was accessed, which we can also use to de-anonymize data. So, that said, these techniques are actually still valuable because they do raise the bar for the attacker. They limit the freedom that you have, and this means that we can do this at a relatively very low overhead. So several of these techniques had very practical overheads compared to especially the mitigations that we discussed before. So all these approaches are not fully secure, but they do add something to security overall.